Check it out now, y'all.
nanoHUB-U online instruction.
Welcome to the last lecture of week 3. Today we're going to summarize what we have learned this week. Well, one of the first things we figure out from learning about the different conductivity or ohmic drop losses in a battery is that in the porous electrode, which is the core of the battery, the losses are a result of the volume fraction of active material and of electrolyte that we have. They are, to a first approximation, described in terms of the porosity associated to the system. So the more porosity you have, the more contributions to the conductivity associated to the electrolyte you have. And if you have an electrode where the particles have a large conductivity, then 1 minus the porosity times the conductivity gives you a contribution to the overall conductivity of that system. Now, because this conductivity depends on the geometry of the system, there is some morphological geometrical term that bundles all the geometry, the complex morphology of the system, and depending on what that morphology looks, we can relate that factor to the tortuosity of the system. So we have perfectly straight paths. That tortuosity has a value of 1. If instead our path bends around as we go from one side of the electrode to the other one, could reach a tortuosity of 2 or a very large value. Okay, or if there is no path to reach the other side, that tortuosity could be infinity. Okay, now if in this case, if the tortuosity can also be seen as the ratio between the average length of diffusion across a thickness h sub c. In this case, it's a statistical measure because, as you can see from this picture, some regions may have longer transport paths than others. Some of them could be straight, and some of them could be even completely blocked. And it is really the statistical averaging of all those contributions that gives you the average tortuosity of the system. If we then take that coefficient to be effectively or to be proportional to that value, then we then assess the fact that really the contribution to conductivity from the active materials is much lower as compared to the contribution to conductivity from the electrolyte themselves. And if you see that contribution, you can neglect that one, and then you can reduce your total conductivity as really depending exclusively on the porosity associated to the system and the tortuosity, that is the way in which these particles are distributed in the system. Now, this tortuosity depends effectively on how many of these obstacles I have. If I have no obstacles, then tortuosity becomes 1. And if I have a very large density of obstacles, this number can be very, very large, dropping significantly the conductivity of the system and therefore increasing the losses that a system will have. Empirically, it has been found that for perfectly spherical particles, smooth particles, the tortuosity can be defined in terms of 1 over the porosity to the 1/2, which was reported by Brugman in 1935 in a paper that had to do more on sands and powders than on anything else. We have used this relationship for many years, and as we move ahead and start detailing the response of the battery, what we find is that really the response of the cell really depends not only on the contributions to tortuosity because of those deviations around the individual particles, but also for what you have, what is the dispersion for the transport of matter in the electrode themselves, which is not really a structureless medium, but actually could have binders, could have a graphite, conductive graphite, and as a result of that, then we found that the total tortuosity of the system really corresponds to the product of all the contributions to tortuosity of the system. In this case, if we have a binary system, corresponds to the product of the tortuosity of the active material particles and the tortuosity of in the electrode itself. If Oh, and of course, then the overall tortuosity, assuming that the tortuosity of the inside the electrolyte also follows a Broussman type of behavior, really will corresponds to the porosity of the entirety of the system. That is the product of both porosities to the 1/2 at the inverse of that. Okay, so we found that. We also found that really the tortuosity really depends on how we make the sample, and it's not the same to have a sample that has a large weight volume fraction of carbon black as compared to one that has very little. Okay, and it's not the same to have particles that have been an electrode that has been mechanically compressed, which would be those electrodes on this side, as compared to electrodes that have not been compressed. If we include then the effect of the carbon black in the system, that can dramatically raise the tortuosity of the system. So whatever inherent tortuosity the particles of the battery may have will be enhanced by the addition of this conductive phase in the electrolyte, which could completely change the response that the system will give you. Okay, now if you consider that, and then actually instead of using the porosity of the active material phase, you actually account for the effective porosity of the system, then you will find that for perfectly spherical particles, you recover back the Broussman relationship. It's a little bit off in this case for this experimental data, but that's mostly as a result of the clustering that the particles can have. Okay, and in this case, it still follows very, very nicely the trend that we have that Broussman initially found many years back. But now we have to account for the individual contributions as to how that material behaves. That, of course, assumes perfect mixing. But what one finds is that really when you actually look at the details, even if you have perfectly spherical particles, if you look at the details as to how those particles are actually assembled in an electrode, you will find that there will be some regions that are poor and that could have a very high porosity, while others will be tightly packed and corresponds to those particles in the middle. Okay, so in fact, it has been found, at least for this set of perfectly spherical particles, that smaller particle size tend to segregate to the edges of the electrode, while the large particles with low porosity will end up being in the core of the battery electrode, suggesting with that really whatever measure could make of macroscopic measure that we make on tortuosity and porosity could be off as a result of the width or thickness of these two layers of small particle size and high porosity. Now, the tortuosity depends not only on how the particles are distributed across the thickness, but actually how they interact. And using this data, we can find that battery particles, the larger body particles tend to segregate to the middle of the electrode, okay, and basically make themselves surrounded by smaller particles, while the particles in the edges tend to be smaller and much more segregated as a result of the lower porosity. So we find that for a classic type of battery, it is very hard to find a perfect ordering, but if you insist on trying to find those batteries that actually deliver a perfect tortuosity in your system, you can using colloidal techniques or other templating approaches, you can define FCC, HCP, BCC, and hexagonal, and indeed you can decrease the tortuosity of the entirety of the system. The effect would really not be seen when you consider primary tortuosity, that is the tortuosity associated to the active material phase only, and you will only see the benefits, if any, when you include the binder phase or if you include the binder phase or the electronic conductive phase. It would be the only way where you could see this difference to shift and actually make a difference, particularly for BCC and FCC. Okay, now in practice, battery materials are not made out necessarily of perfectly spherical particles. In fact, making perfectly spherical particles is very hard to do. Instead, what we find is that particles are made out of different shapes, morphologies, and sizes that all combine themselves to basically define effectively how this electrode will react. Okay, what we find is that the spherical particle will give you the highest density as to how much you can pack the structure, the area density, while these other particles will give you a much larger energy density if you manage to compact them very tight. So if you use this type of structure, what you will find is that to a first approximation, the Bridgman relationship is valid and works very well. Okay, but if you want to account for materials that have an increasingly larger morphological anisotropy, the particle interactions will lead to a three-dimensional state of tortuosity in the system. So outside the plane, which is the direction that people typically use for better response, could have a tortuosity that could be much larger than the Bridgman ideal, and even that anisotropy will alter the in-plane tortuosity within the cell. Okay, and that will of course make that the region that you use the most is actually the region that has the highest losses, and the ones that where really lithium is just distributed laterally would actually have the lowest ones, but it's not the ones through which we are counting our the charge that we're using. So if we increase further the tortuosity of the system, and in this case we have very large aspect ratio particles, in this case is graphite, you will find that actually the tortuosity becomes a function of a very strong function of the porosity. So for as you come down to a very low values of porosity, you can go from a tortuosity that has a value of 1.5 to say 3 times that number, which or more, which in this case becomes a value of 6. Okay, and in this case you should be able to pack more particles as this aspect ratio allows for less interstices to be left behind, but the perfectly spherical particles will always stay down here. So there's some benefits and drawbacks. The benefits of having perfectly spherical particles is that you will indeed can have a high reactivity per unit area, and be able to, but not be able on a lower tortuosity, while the high aspect ratio structures will allow you to pack more material, but the losses will be much more higher in comparison. Now, there are other additional contributions to tortuosity, correspond to the tortuosity as they're being delivered by the separator itself. Okay, and in this case, people tend to make separators as small as possible in order to be able to decrease the losses as ions are going from the anode to the cathode or back. Okay, and in this case, when Thorad and Wheeler measured the tortuosity as a function of thickness, of total thickness of separators, they found that the overall tortuosity was non-zero in the limit of 0 separators, but instead they found that in a very, very small distance you can have a tortuosity value of 4.8, which if you take the thickness average of each of those contributions can come down all the way to basically 2.5, but still it will be a very large value and can rapidly limit the high power density performance of the cell. Okay, all these contributions, the ones in the separator, the ones in the cathode and anode, the morphology that you impose, how you process them, and how each of these contributions is being packed together will have a very important effect on the sum of all the losses occurring between the two back contacts in the cell sandwich. So there are some, in this case, conflicting accounts as to what the dependence to tortuosity for the separators are. And so while, for example, Abraham proposes that the tortuosity goes to 7.3 over epsilon, Dijon and Patel have relationships that go over 1 over epsilon to the 2.46 or 2.8, suggesting really here that you have, there's a lot of space still for improvement, and especially on the separator part, for both decreasing the losses and increasing the conductivity of the system. Thank you.